Hi, I'm Bjorn Turius, and I'm here to present part 3 of my video series on process control. In parts 1 and 2, we looked at the steady state and dynamic aspects of the simple process I've chosen for the Control Concepts app. In this video, we continue to explore the characteristics of the process by way of what's called frequency domain dynamics. It'll be slightly more theoretical in nature than the first two parts, but the concept we introduce here will be very useful when we look at feedback control performance in later videos. The frequency response of most processes is defined as the steady state behavior of the system when forced by a sinusoidal input. So here's a process, and it's being forced by a sinusoidal input. Draw it here. With frequency omega. The output will also be a sine wave with the same frequency, but typically the output sine wave is slightly delayed in time and it has a lower amplitude. So here's the output. Here's a pre-drawn diagram of two sine waves. These two sine waves can be viewed as being generated by the tips of the two hands of an imaginary clock. The clock is peculiar in the sense that the two hands are stuck together with a certain angle theta, as shown here in the diagram. If we plot the hand's vertical position versus time as the hands move counterclockwise, we get the two sinusoidal curves shown in this figure. The two little dots on the curves are the vertical positions of the hands at this very moment of the rotation. The green dot, as you can see, is close to the top of its curve, while the purple dot still has some time to go before it reaches its peak. The hands on this imaginary clock move one full rotation in t hours. That traces out a full period for both curves. The frequency, omega, is then 1 over t periods per hour. A complete rotation is also 360 degrees, or 2 pi radians. Just as a reminder, a radian is a unit of angle equal to an angle at the center of a circle whose arc is equal in length to the radius. Another measure of frequency is therefore 2 pi over t radians per hour. That measure is particularly useful in process dynamics since the time constant and the dead time of a process measured in hours have simple relations to the frequency when it is measured in radians per hour. The difference in time for the two curves to reach the corresponding position is denoted as t sub x, hours. This time lag is most easily seen when the curves cross the baseline. Tx is proportional to the phase shift theta by the simple formula shown here. With the imaginary clock in mind, it's easy to realize why this has to be true. That's how we can express the observable phase shift as an angle. If we assume that the green input curve has an amplitude of m units and the resulting output curve has an amplitude of x units, we can easily calculate the magnitude ratio mr as x over m. The magnitude ratio is most conveniently expressed as the log modulus, which is defined as 20 times the log 10 of the magnitude ratio. The log modulus has units of decibels. The simulator has built-in provisions to do frequency analysis. The sinusoid comes in with a disturbance stream, and its properties are set from the configuration panel as seen on the screenshot. Please note that the heated stream is still flowing and has a constant temperature of 50 degrees. Thus, an amplitude of, say, plus minus 40 degrees on the disturbance stream is reduced to plus minus 20 degrees after blending with the heated stream. We put the tank TC in manual. We set the output to 34.5. We set the level at 50%, which it's already at. We only need one chart, so let's get rid of the second chart here by edit, clicking on that chart, trash can, done. We need to set the sine wave generator on. We will start out by setting the frequency to 0.5 periods per hour, and we'll have an amplitude of 40 degrees, which is 40% of the span, which is 100 degrees. We're done, and let's see what happens. The green curve is the disturbance stream, and it's going to show plus minus 40 degrees as we set it. But remember, when it blends with the heated stream, it's going to result in plus minus 20 degrees. So that's the maximum that the tank can attain. The blue curve is the tank temperature, and you can already see in the simulation here that the green curve reaches the zero line there, and the blue curve lags and comes up there and crosses the line. So we have definitely a little bit of lag between the two curves. We can also see that the blue curve is barely coming up to 20 degrees, and therefore there's a little bit of attenuation, but not much. Let's try another frequency. We're going to put in 0.87 periods per hour. But we also immediately see that there is more attenuation because the blue curve peak is not as high as it was for the previous frequency. So let's try yet another frequency, 2 periods per hour. And it's pretty clear that attenuation is much more pronounced at this higher frequency. So the peak of the blue curve is not nearly as high as it was before. And let's see if this trend continues. We'll put in yet another frequency, higher frequency of 4 periods per hour. The attenuation is clearly more pronounced again, and the amplitude is fairly low now on the tank temperature. Okay, let's now go back and review these curves in a little bit more detail. I've taken screenshots of them previously, and we'll go back and analyze them. I've annotated screenshots of the 4 runs we made, and we're going to calculate the log modulus and the phase angle for each case. We do that from the amplitude ratio of the curves and the time delay between them. Let me point out that this information can be calculated from just knowing the time constant in this particular case. Frequency analysis doesn't provide any new information about the process over and above knowing the time constant at dead time. It simply provides a different view of the dynamics, but one that's very useful for feedback control. The first case was at 0.5 periods per hour. It's of course impossible to determine x, the peak of the blue curve, and tx, the time difference between the curves, with any accuracy from these plots, but since it can be calculated exactly from knowing the time constant, I put the correct values in, and you can validate that these values must be right by inspecting the charts. The tank temperature peaks at 17.4 degrees centigrade, and therefore the magnitude ratio is 0.87, making the log modulus minus 1.2 decibel. The time shift between the curves turns out to be 0.17 hours, which translates to minus 30 degrees phase angle. In case 2, we ran that at 0.87 periods per hour, which is 5.47 radians per hour. The inverse of that number equals to 0.18, which is the time constant of the tank when 50% full. That is the simple relationship between time constant and frequency that I mentioned earlier. The log modulus for this case is minus 3 decibels, and the phase angle is minus 45 degrees. The next case is for frequency equal to 2 periods per hour. The log modulus is minus 8 decibels, and the phase angle is minus 67 degrees. It's perhaps surprising that the phase angle keeps increasing even though the time distance between the two curves is shrinking. The reason is, of course, that the time for a complete period decreases even faster than the time distance between the curves. In the final run, the log modulus is minus 13.6 decibels, and the phase angle is minus 78 degrees. And this was for a frequency of 4 periods per hour. The results are summarized in this table. We can plot the log modulus and the phase angle versus the log of the frequency measured in radians per hour, and we can get a so-called Bode plot. So here's the log modulus versus frequency, log of frequency, and here's the phase angle versus log of frequency. And you can see here the point of 1 over the time constant that I mentioned before. That was our second data point that had a phase angle of minus 45 degrees and a log modulus of minus 3 decibels. So that is typical of a first order lag, which is exactly what the tank is when we measured it. We did not measure or test the ion exchange column in this test because the sinusoidal feed disturbance went in directly to the tank and not through the ion exchange column. But it's pretty easy to construct a dead time element, or a Bode plot of a dead time element. It turns out that it has no change in the log modulus with frequency, but a direct change of phase angle versus frequency, such as shown here. So the plot I have is for a dead time element of 0.2 hours in this case, and you can see that the phase angle dips down pretty far and pretty fast with frequency. So even at the low frequency, the phase shift starts to be significant, and that has great implications for feedback control.